Greetings, everyone. Welcome to another episode of the Organic Chemistry course. Today we are covering hydrocarbons, the AS section of hydrocarbons. So let's get started. So, what are hydrocarbons? Hydrocarbons are organic compounds made of carbon. Let me get my pen there. Made of carbon and hydrogen as the only elements. Hydrocarbons are organic compounds made from carbon and hydrogen only, right? So under hydrocarbons, from the previous topic, you saw that we had alkanes and alkenes. So let's start with alkanes. So alkanes, what I was saying there is that they're generally unreactive, right? They do not react with acids, bases, and are unreactive towards polar reagents. There's this saying in chemistry which says polar reagents react with other polar reagents, and non-polar reagents react with other non-polar reagents. So since alkanes are non-polar, that is what contributes to their unreactivity. As I said in this statement, to say the reason for their unreactivity is due to the similarity in electronegativity between the carbon and hydrogen atoms, right? Therefore, alkanes are non-polar. Alkanes undergo two types of reactions that we're going to cover on this topic, which is one being combustion and halogenation. So let's get down to them. So now let's talk about combustion. Alkanes undergo complete combustion to produce carbon dioxide and water as the only products. Okay, that is when we're talking about complete combustion. So in this first equation there, it's not really balanced. It's not balanced really, but it's just for illustration purposes. The second one is balanced. All you need to do is you take your alkane, add your oxygen, produce carbon dioxide as the carbon dioxide and water as the only products, then you balance the atoms. That's all there is to it. Moving on to halogenation. Alkanes react with halogens in the presence of UV light to undergo what is called a free radical mechanism, right? In the free radical mechanism, the reaction takes place in three stages. There is the stage that is called the initiation, right? In the initiation stage, UV light breaks down the halogen into what are called the radicals here. I think in the previous video I spoke about radicals being atomic species, right, with an unpaired electron. So UV light here causes this to happen, right? It produces, for example, if the halogen is chlorine, it produces chlorine radicals. Now the next stage, that is the second stage of the free radical mechanism, is called the propagation stage. In the propagation stage, what happens? The radical is added with alkane as an example to produce, here HCl is produced plus another radical, a methyl radical. The methyl radical can also react with another halogen to produce what? Another chlorine radical. And the stage can go on and on and on until here you see this monochloroethane. This propagation stage can go on and on until CCl4 is formed, which is called tetrachloromethane. So the propagation stage, there's no hard or fast rule to say what really happens, but what happens is this: a molecule reacts with a radical to produce another molecule plus another radical, and the reaction goes on and on until something like this is formed. We shall be doing a lot of tutorial questions, and I shall be showing you different ways in which this propagation can occur. Okay. Now the last stage of the reaction is called the termination stage. In the termination stage, radicals combine to produce molecules. Like as you see here in the first reaction, we've got chlorine radicals reacting to produce a chlorine molecule. Here we've got methyl radicals combining to produce what? Ethane. Now here we've got a CH2Cl radical combining with the CH3 radical to produce monochloroethane in third reaction. So those are type of termination reactions that can occur, but for you to understand, this is just this. Radicals are combining to form molecules. The reactivity of halogens with alkanes decreases down the group from chlorine to iodine. You know that halogens are oxidizing agents, and their oxidizing power decreases as we move down the group. That's all there is to it. Okay, now let us talk about alkenes. Alkenes are very unreactive because they have a double bond, a region which is rich in electrons, right? And can easily be attacked by an electrophile. An electrophile is a negatively loving species. So the double bond of alkenes is very electron rich. Hence the double bond of alkenes is very electron rich. That's why you find out that they are an electrophile likes to attack those electron rich areas. Okay, now let's get down to business. Now you must understand that alkenes undergo four types of reactions. Or let me just say, those reactions are similar. They are addition reactions. For example, you can add steam. For example, addition of H2, right? Also of hydrogen, addition of H2. This is my alkene in here, reacting with hydrogen in the presence of a nickel catalyst. The catalyst can be nickel, it can be platinum, or it can be palladium, right? At a temperature of 150 degrees Celsius and 4 atm pressure to produce an alkane. That's all there is to it, right? So I just wrote a statement there to say this reaction is also used in the formation of margarine from vegetable oils, hardening of vegetable oils to produce fats. I don't know if you're well aware of that kind of reaction, but it's okay. If you're not familiar with it, it's okay. You can let it go. It was just a nice to know statement. The next reaction is the reaction with the steam. It's an addition reaction as well. We have got an alkene here there, adding steam to that alkene in the presence of what? Phosphoric acid and at a temperature of 300 degrees Celsius to produce an alcohol, right? So the phosphoric acid there is a catalyst working at a temperature of 300 degrees Celsius. Okay, so let me change the color there. I think I prefer which color? This one. Yeah. So now, this is just a reproduction of the page. Okay. Now let me talk about addition. First, let me start with this one. Is my third one. Then I'll come back to the top. Okay. Okay. Let me start with the one in the top. No problem. So, addition of a hydrogen halide. The hydrogen halide here, let me call it as HX. Right? When a hydrogen halide is adds across a double bond, the hydrogen atom of the double bond adds to the carbon atom that already has a large number of hydrogen atoms, which is the Markovnikov's rule. What is it saying here? Now let us look at this. This is the carbon atom of the double bond, and the other one is here. This one is one hydrogen atom, and this one here is 2, right? So when we add a hydrogen halide, let me call it an HX instead of Cl, where X here is equals to chlorine, bromine, or iodine, right? When we add an HX bond here, so this is HCl, we replace it for HX there, and this Cl for HX here. So what happens is this side here has got 2 hydrogen atoms, and this one is 1. According to Markovnikov's rule, this hydrogen here shall add to the carbon atom with more hydrogen atoms, right? So you're going to see that in this reaction, 2 mixtures, 2 isomers are produced, this being the first isomer, this one being the second one, right? But the one that favors Markovnikov's rule will be existing in larger amounts. For example, according to Markovnikov's rule, this is a likely scenario the likely scenario here. So you'll be having this isomer existing as, let's say 95%, and this one is 5%. That is Markovnikov's rule for you. So you must know. So you must just know how Markovnikov's rule works. So Markovnikov's rule is just revolves around what they call stabilization of the alkyl groups. Right? How alkyl groups stabilize the cations. I shall do a separate video on just on Markovnikov's rule. But I just want you to understand Markovnikov's rule in the light that I just put it right now. I hope you understand. Now, addition of halogens. For example, you've got an alkene, then you add the halogen Br2 there, right? Br2 there, you produce a dibromoalkane. In this reaction, bromine is decolorized. Reactions with halogens are called halogenation, but to be more specific, in this type of reaction, it's called a bromination since we're adding bromine. Right? And this there I wanted to say halogenation, this was a mistake. Mechanism of halogenation of alkenes. So you see what happens here. We've got this the double bond here that we have here polarizes this halogen molecule in such a way that it repels electrons from this chlorine atom to the other side, so that this one becomes negative and this one positive. Right? What then happens now? It causes heterolytic cleavage to take place in such a way that we now have an electrophile here, a negatively charged electrophile there, which then attacks the positively charged region to become a what? A dihalogenal alkane. Yes, dichloroethane. Dichloroethane, yes. So this is the same mechanism that is just example being repeated below, using ethane as an example. Here this was not ethane, but we've got other groups there. It can be anything. You can even have a benzene ring there. You can even have a benzene ring here, even though in AS benzene rings are, I don't think they're common. Just a minute. Right? Anything, it can be anything, right? Maybe you can have a CH3 there. That's why I did not put anything there. But in the second example, it was purely ethane. So it was a dihalogenal alkane. That's the best way to call it, since we were not given the other 4 species there. So there I was just explaining how the theory of how this thing works, okay? Which I just explained. Now let us talk about the reactions of alkenes with cold dilute potassium manganate. Alkenes react with cold dilute potassium manganate to undergo an oxidation reaction to form a diol, right? This potassium manganate changes color from purple to green. So what happens? We have an alkane reacting with cold dilute acidify the potassium manganate to produce a diol. This is a diol. Hope you get it. So this reaction is used to test for alkenes. The reaction of Br2 with alkenes can also be used to test for alkenes. So this is just a nice to know statement to say alkenes are tested using Br2 in tetrachloromethane. Right? Another type of reaction that takes place there is the reaction of alkenes with what concentrated potassium manganate. Right? So alkenes react with what acidified potassium manganate, causing a rupture or a breaking of the double bond. Right? So leading to the formation of carboxylic acids, a ketone, or even carbon dioxide. So you're going to find out that I have the first reaction that I have here, 1, right? As you go down, I have the second reaction and the third reaction, and all of them are producing different products. So how do you know which product comes out? Excuse me. And now I have this carbon here is attached to 2 hydrogen atoms. That is what causes carbon dioxide in water. Now, if the carbon of the double bond is 1 other group and 1 hydrogen atom, it forms a carboxylic acid, right? If you go down, if the carbon of the double bond has got two other groups like this leads to the formation of a ketone. And still this one, as the first example, leads to the formation of what? Carbon dioxide and water. I hope you are getting it. Now this one as well as the second example has got two other groups, leads to the formation of a ketone. Now this one's got one other group, CH3 plus one hydrogen atom, that leads to the formation of a carboxylic acid. So how do you know now? How do you know now the coefficient? Maybe let's say you're in an example, right? You've forgotten the coefficient of the oxygen there. You just make sure you produce your products first. You know, it has one hydrogen atom, that is the one. This one the second one. This one the third. Then the coefficient is 3 there. That's all. So we're almost done with the AS section of this topic. Now I want to talk about the uses of crude oil as a source of aromatic and aliphatic hydrocarbons. In AS, we're not really concerned about aromatic hydrocarbons, but these are just hydrocarbons which contain a benzene ring. Aliphatic hydrocarbons, these are just straight chain alkanes. So we are saying all these are found from crude oil. That's all, right? So crude oil is a mixture of different hydrocarbons. It's a mixture of hydrocarbons with different boiling points. They can be separated by fractional distillation into their different compounds or components. Crude oil is a source of aromatic and aliphatic hydrocarbons. Right, that's what I was just saying. But crude oil can also be a source of cyclic hydrocarbons. Cycloalkenes, yes. So now there's a process which is called cracking there, which is a process whereby we take long chain alkanes of higher molecular mass in order to convert them to shorter chain alkanes of lower molecular mass, which are useful. During cracking, an alkane or an alkene are produced. When cracking is done in the presence of a catalyst, it is called catalytic cracking. So you must understand that alkenes are, for example, cracking is the process that we use to generate alkenes actually most of the time, right? So that's the statement that I wrote there last, to say alkenes are very important because they are very reactive and are used as starters for the synthesis of other products. Right? Let's talk about the uses of alkanes. You know these guys. To say alkanes are used as transporting fuels, as fuels for industry and homes. Yes, those are the main uses of alkanes. Which brings us to I think this brings us to the end of the AS section under environmental consequences of using fuels. So when fuels are burned, incomplete combustion may occur. Right? Incomplete combustion may occur. So when incomplete combustion may occur, carbon monoxide is produced, and you know that it is a pollutant which causes breathlessness, right? So for this cause, let's say for cars are the greatest emitters of where the greatest emitters before the introduction of the catalytic converter. When the catalytic converter was inserted into cars, what happened? For example, they are saying that when this catalytic converter, before them, cars used to emit carbon monoxide and the oxides of nitrogen, which cause acid rain. But when catalytic converters were embedded into cars, they caused these. You must understand that. Let me show you the best way of how a catalytic converter works. In a catalytic converter, the carbon monoxide, oxides of nitrogen, these can either be NO or NO2. They are fed into the catalytic converter, producing nitrogen, pure nitrogen, and carbon dioxide, which are less harmful. This is what a catalytic converter does, right? That's all I was trying to say in the literature there. So I don't have to say a lot of things to complicate the issue, right? And under the topic inorganic chemistry and hydrogen itself, I covered this in more detail. This was just a repetition. So guys, this brings us to the end of this video. I hope you found it useful. And if you liked this video and would like to support the channel, please comment, like and subscribe, and I'll see you all next time. Thank you.